The universe has existed for about 13.8 billion years, and it is still expanding. Yet a new model suggests that this expansion may not continue forever. Welcome to Night Cosmos Sleep. On tonight's journey, we will follow the light of distant galaxies, where scientists are beginning to find the faintest signs of a very different future, one in which space slows down, comes to a complete stop, and then begins to collapse back in on itself. From those almost imperceptible deviations, a number has emerged, roughly 33 billion years for the entire lifespan of the universe, if this model proves to be correct. It is a number large enough to open a question that once seemed impossible to answer. Could the universe itself be living within a finite span of time? The universe has existed for about 13.8 billion years. Ever since human beings first looked up at the sky and realized that those points of light were more than lamps suspended from a celestial dome, our greatest questions have usually turned toward the beginning. Where did everything come from? How did space open up? And what happened in those earliest moments, when the universe was hotter and denser than any state we can truly imagine? Recently, however, a group of physicists has tried looking in the opposite direction. Rather than asking only how the universe began, they have explored the possibility that all of space may have a finite lifespan, a span long enough to contain every galaxy, every star, and every story that has ever appeared, yet one that may still eventually reach an end. When new observational data were placed within a model of dark energy that changes over time, a number emerged, about 33 billion years. This is not the remaining lifespan of Earth, the Sun, or any individual galaxy. In this model, 33 billion years represents the total lifetime of the universe, measured from its beginning to the moment when cosmic expansion may reverse and move toward a state of collapse. At first, this idea seems completely at odds with what we observe. The universe is not contracting today. It is still growing. Galaxies that are sufficiently far apart continue to move farther away from one another, not necessarily because they are all flying outward from a central point, but because the space between regions no longer held tightly together by gravity is itself expanding. A galaxy can still hold on to its stars. A planetary system can continue orbiting its central star, and the atoms in our bodies are not being stretched along with space. Expansion becomes apparent only across distances large enough to exceed the scale of systems bound together by gravity. From our present perspective, every sign still indicates that space continues to expand. In fact, this expansion was discovered to be accelerating. For many years, that picture pointed toward a future with almost no final boundary. Galaxies drifting farther apart, light from distant regions gradually becoming unable to reach us, matter growing thinner, and the universe slowly cooling. That would not be an ending that arrives at one specific moment. It would be more like a fading that continues almost without limit. Yet the new model does not deny that expansion is happening. It simply asks whether the speed and direction of that process could change in the very distant future. According to the set of parameters that best fits the researchers' calculations, the universe may continue expanding for another 11 billion years. That span is more than twice the current age of Earth. Long enough for many generations of stars to be born, shine, and disappear. Throughout that time, space would continue to grow, but the force driving its expansion might not remain constant, as we once assumed. The rate of expansion would gradually change, slowing across intervals so immense that no civilization could ever observe the entire process from beginning to end. Eventually, the universe would reach the largest size allowed by the model. There would be no wall at the edge of space and no warning sign appearing in the sky. The remaining stars would continue to burn, planets would keep moving, and light would still travel through the darkness as before. Only the universe as a whole would have reached a special turning point. The distances between extremely remote regions would no longer increase. Beyond that point, the process could reverse. Space would not collapse instantly like a room being compressed, nor would every galaxy suddenly turn and rush toward a single central point. Instead, the scale of space itself would begin changing in the opposite direction. Distances that had grown for billions of years would slowly begin to shrink. At first, the contraction might be so slight as to be almost impossible to detect, but once the overall direction had changed, the density of matter and radiation would begin to rise. The universe, which cooled as it expanded, could then gradually warm as it contracted. As the process continued, the collapse would grow more intense, drawing matter, light, and every surviving structure into an increasingly smaller volume of space. Under the set of parameters being considered, this phase would last nearly 9 billion years before reaching the Big Crunch, a state in which the universe becomes extraordinarily hot and dense. From the present day, that final point would lie roughly 19 to 20 billion years in the future. Added to the 13.8 billion years that have already passed, the total lifetime would come to nearly 33 billion years. That would mean that, if the model is correct, the universe has already passed through more than 40% of its life, even though the time remaining would still exceed any timescale familiar to human experience. Numbers like these can easily create the impression that the end has been calculated with the certainty of a clock. In reality, the situation is far more cautious. No telescope has seen the Big Crunch, and no instrument can directly observe an event tens of billions of years into the future. The figure of 33 billion years appears only after researchers choose a particular model, adjust its parameters to fit present-day data, and then allow the equations to continue running forward in time. If the model accurately reflects the nature of dark energy, that path may carry the universe toward a turning point. If the original assumptions are wrong, the entire picture could change. The universe might continue expanding for far longer, or it might never contract at all. So this is not a declaration that the final day of space has been discovered. It is a possibility under investigation, opened by several small deviations in new observational data. The source of this uncertainty lies in dark energy, the name we give to the unknown cause that appears to be driving the accelerating expansion of the universe. Dark energy does not appear in a telescope as a cloud or a glowing object. Scientists recognize its influence by tracking how the distances between galaxies change over time. In the simplest model, dark energy remains constant. As matter becomes increasingly diluted within an ever-growing universe, this component keeps the same influence and eventually dominates the future. If that assumption is correct, expansion will continue forever. Recent measurements from maps of galaxies, supernovae, and the cosmic background, however, allow for another possibility. What we call dark energy may not be completely unchanging. Its influence in the past may have been slightly different from what it is today, and that very small difference is enough for physicists to begin constructing new models. One of these proposes that dark energy may contain two components. One changes extremely slowly over time, so slowly that the age of the universe itself must be used as the clock by which it is measured. The other is an underlying energy with a negative value. At present, the changing component is still strong enough to conceal the negative contribution beneath it, so the combined effect continues to make space expand. Over billions of years, however, that balance could shift. As the positive contribution weakens or changes state, the negative background would gradually become more important. The universe would not stop immediately, just as an object thrown upward continues to rise even as its speed decreases. Only when the momentum of expansion had gradually faded would space reach its maximum size and begin to contract. This is how the model connects a very small deviation in today's data to an ending tens of billions of years in the future. Even so, neither the changing component nor the negative energy background has been observed directly. They are explanations proposed by the model, not objects that have been discovered in the universe. So how can a measurement made today tell us anything about a future so unimaginably distant? The answer does not begin by looking directly ahead. It begins with light that has traveled through the past. When a galaxy lies billions of light years away, the image reaching our telescopes is not an image of that galaxy as it exists today. Its light left long ago, sometimes before Earth itself had formed. Each distant galaxy, therefore, serves as a marker located at a different moment in cosmic history. Looking deeper into space also means looking farther back in time. The sky is not only spread across distance, but arranged in layers of history. The figure of 33 billion years does not come from some enormous clock counting down somewhere in space. It begins with tiny points of light, with colors stretched during journeys lasting billions of years, and with the way millions of galaxies are distributed across a vast region of the universe. As the universe expands, the wavelengths of light are stretched along with it. The amount of that stretching, usually measured through redshift, helps scientists estimate how much space has changed between the moment the light left its source and the moment it reached us. A single galaxy provides only a very small piece of information, but when millions of those pieces are brought together, they begin to reveal the expansion history of the universe as a whole. A telescope does not see a 33 billion year lifespan. It records light, redshift, distance, and large-scale patterns in the distribution of matter. From those observations, researchers try to reconstruct how the universe has grown through different eras. If a model can accurately reproduce the history we have observed, it can then be allowed to continue forward into the future. Some paths expand forever. Others gradually slow and eventually come to a stop. In the case being considered here, the path of expansion reverses and leads toward a big crunch. This is an extrapolation based on what we know, not a direct observation of the future. For that reason, the number may still change as new data become available. The signs that dark energy is evolving may become clearer, but they may also fade as uncertainties are reduced. The differences seen today could be traces of new physics, or they could simply result from the way several datasets have been combined. A model involving an ultralight axion and a negative cosmological constant may provide a fitting explanation, but it is not necessarily the only one. What matters is not that science has confirmed a date for the end of the universe. What matters is that a very small deviation in the light of distant galaxies has been enough to reopen a question that once seemed settled. Will the expansion of the universe truly continue forever? To understand where space may be heading, scientists must first retrace how it has grown, and to do that, they are turning millions of galaxies into landmarks on a three-dimensional map, where every position reveals not only where an object lies, but also preserves a moment in the history of the universe. When we look at a galaxy billions of light years away, we do not see it as it exists today. The image entering the telescope is an older version, sent out long before its light completed the journey across space. Some galaxies appear in the data as they existed before Earth had even formed. The sky, then, does not merely extend across distance. It also preserves time. Every deeper view carries us farther into the past. A nearby galaxy reveals a relatively recent era, while a very distant one bears traces of a much younger universe. By determining the positions of enough galaxies across enough distances, scientists can create more than a map of where matter is located. They can layer many periods of cosmic history into a single picture. That is what projects such as DES and DESI are working to accomplish. DES, the Dark Energy Survey, observes broad regions of the sky to record the shapes, brightness, and distribution of galaxies, while also tracking stellar explosions that can be used to measure distance. DESI takes a complementary approach. It gathers light from vast numbers of galaxies and quasars, separates that light into smaller components, and searches within it for clues revealing how far away each object lies. DESI does not need to photograph every galaxy in the way an ordinary camera captures individual faces. Its main task is to collect light from thousands of objects during a single observation. Each source contributes only a tiny amount, but when millions of measurements are placed side by side, they begin to form a structure far larger than any single image. From points that once seemed disconnected, a three-dimensional map gradually emerges. The first two dimensions are familiar. They tell us where a galaxy appears on the sky. The third is harder to see because it represents distance. Two galaxies may look close together from Earth while actually being separated by billions of light years in depth. To place each point in its proper position, scientists must read the information carried within the galaxy's own light. Light can be imagined as waves moving through space. Each color corresponds to a different range of wavelengths. As space expands while light is traveling, those wavelengths are stretched along with it. Light originally emitted at a particular position in the spectrum appears shifted toward the red by the time it reaches us. This shift does more than change color in the ordinary sense. It acts as a trace of how much the space crossed by the light has expanded. In general, the greater the redshift, the farther back in time the light began its journey. This allows scientists to estimate a galaxy's position along the depth of the map while also identifying the period of cosmic history they are observing. A single measurement always has limitations. Galaxies have motions of their own, light can be influenced by the surrounding environment, and every observation carries some degree of uncertainty. The goal, therefore, is not to use one point of light to tell the entire history of cosmic expansion. The real strength appears only when the number of measurements becomes large enough for individual fluctuations to fade into the background, leaving behind a broader trend. Millions of galaxies become millions of markers. Some are relatively nearby and reflect the universe at a later stage. Others lie much deeper in the past. When placed in their proper positions, they form an immense network of dense regions, vast empty spaces, and long strands of matter stretching between them. On the largest scales, the universe is not distributed like a uniform mist. Galaxies gather into groups, clusters, and elongated filaments surrounding enormous voids. This structure is often described as the cosmic web, but it was not created randomly in the present day. The form we see now is the result of tiny differences that were already present when the universe was young. In the beginning, matter was distributed almost evenly, but not perfectly so. Some regions were slightly denser, while others were slightly thinner. Gravity gradually amplified those differences. Matter was drawn toward places that were already a little denser, while regions containing less material became increasingly empty. Over billions of years, those small variations developed into galaxies and galaxy clusters. Although that history is extraordinarily complex, it still preserves a distinctive pattern from the early universe. Before stable atoms formed, matter and light moved through a hot, dense environment where pressure and gravity created waves that traveled outward. Those waves left behind a characteristic distance in the later distribution of matter. It can be imagined as the faint imprint of old ripples on water, even though the original surface has long since changed. Scientists do not see those primordial waves still moving through space today. Instead, they recognize their trace in the slight tendency of galaxies to appear separated by one particular distance more often than by others. That characteristic distance acts as a standard ruler. The ruler was formed very early, and its original length can be estimated from the physics of the young universe. By observing it at different periods, scientists can see how space has stretched it over time. If the measured distance is larger during later eras, that difference reveals how much the universe has expanded. This is not a physical ruler lying intact between two particular galaxies. It appears only in the statistics of an enormous number of galaxies. Any single pair tells us almost nothing, but when millions of pairs are examined, one separation begins to occur slightly more often than the others, a signal so subtle that only an immense map can reveal it. Deci uses this delicate pattern to trace cosmic expansion across many different eras. Galaxies at different distances reveal the standard ruler at different moments in history. By comparing them, scientists reconstruct a path showing how the growth rate of space has changed over time. Each layer of data is like a single frame in a film unfolding across billions of years. Des adds other perspectives to the story. The shapes of galaxies can be distorted ever so slightly as their light passes through regions containing large amounts of matter, producing an effect known as weak gravitational lensing. Those tiny distortions help trace how matter is distributed, including matter that emits no light. Supernova explosions also allow scientists to compare observed brightness with intrinsic brightness, providing another way to measure distance. Each method has its own strengths and limitations. Redshift helps place galaxies within a three-dimensional map. The standard ruler reveals how the scale of space has changed. Supernovae trace the relationship between distance and brightness. Gravitational lensing shows how matter has gathered under the influence of gravity. No single measurement can tell the entire story on its own. When several independent methods are placed side by side, they help determine whether the same expansion history appears in each one. If the results agree, confidence in the overall picture grows. When they differ slightly, that discrepancy may point to uncertainties that are not yet fully understood, or suggest that something is missing from the model being used. What Deci actually sees is still only light. It does not photograph dark energy, reveal an invisible field stretching space, or directly observe the force that may shape the future. Dark energy is recognized only through the influence it may have left on changing distances and on the rate at which large structures formed. We might imagine a river whose current is difficult to see in the darkness. Leaves drifting across the surface would reveal the direction and speed of the flow. Galaxies are not simply leaves being carried along by dark energy, but their motions and distribution still contain information about the cosmic background in which they exist. As the map grows larger, random fluctuations begin to diminish. A galaxy may have its own motion, slightly distorting a measurement. One region of the sky may contain fewer objects purely by chance. An instrument may also be more sensitive under certain observing conditions. A vast amount of data helps scientists identify and reduce the influence of these effects. Yet more data does not automatically guarantee a correct answer. A small error repeated across millions of measurements can still create a false trend. The selection of galaxy samples, the calibration of brightness, the measurement of redshift, and the combination of different surveys must all be examined carefully. Science is searching for a very small change within a picture so immense that even a subtle shift can alter how we understand the future. When the first results were placed onto the map, most of the universe still behaved much as the familiar model predicted. Galaxies appeared in positions broadly consistent with a history described by dark matter, ordinary matter, and a constant form of dark energy. There was no obvious breakdown and no entirely new curve replacing everything that had come before. There was only one detail that did not fit perfectly. When DESI data were combined with other measurements, the history of cosmic expansion appeared to allow dark energy to change slightly over time. The signal did not appear as one isolated anomaly. It emerged in the way several layers of data leaned subtly away from the path predicted by the simplest model. The deviation remains small, and its significance changes depending on which datasets are combined. Some combinations make the signal more noticeable, others weaken it. This is not enough to say that dark energy is definitely evolving, but neither is it as easy to dismiss as an insignificant fluctuation. If distances in the past truly do not match a constant form of dark energy, then the force driving expansion may have changed over time. Even so, the same discrepancy could still have several explanations. It may come from data that have not been perfectly calibrated, from the way different surveys are connected, or from a model of matter and large-scale structure that still needs adjustment. The map has not delivered a verdict. It has only brought the question into sharper focus. The main outlines still resemble the older picture, but a few distances seem to lie slightly away from where they were expected. A very small difference in the present may require only a minor adjustment to the model. Yet, when extended across tens of billions of years, it could also lead to a completely different future. For many years, the simplest explanation held that dark energy does not change. If that is true, its influence will continue to dominate as matter becomes increasingly diluted, and the universe will never turn back. Space will keep expanding, galaxies will grow farther apart, and the future will stretch toward a state that becomes ever colder and emptier. Before following the new deviation and seeing where it might lead, we first need to understand why that ending once seemed almost unavoidable. The entire belief in a universe that expands forever rests on one very simple assumption: that the force causing space to grow today will remain unchanged through every tomorrow. Gravity always pulls matter together. It keeps the moon in orbit around Earth, holds the planets around the sun, and gathers billions of stars into vast galaxies. So when scientists first learned that the universe was expanding, the natural question was whether the combined gravitational pull of all its matter might be strong enough to slow that expansion down. Perhaps space would continue to grow for a while, and then gradually lose momentum. Perhaps galaxies would move apart more slowly, until expansion finally came to a stop. If there were enough matter, gravity might even pull everything back together. For a long time, the future of the universe seemed to depend on that balance. On one side was the expansion that had begun in the early universe. On the other was the pull of matter, always working to hold structures together. Then, observations revealed something entirely different. Space was not merely continuing to grow, its expansion was accelerating. The first signs appeared when scientists observed extremely bright stellar explosions in distant galaxies. Certain kinds of supernovae have sufficiently consistent brightness to serve as reference points. By knowing how bright an explosion should be, and comparing that with how bright it appears from Earth, researchers can estimate its distance. The light from those explosions had traveled through space for billions of years. During that journey, its wavelengths were stretched by cosmic expansion. Brightness revealed how far away the explosions were, while redshift showed how much space had changed since the light left its source. When the two measurements were compared, the galaxies appeared farther away than expected in a universe whose expansion was slowing down. The simplest explanation was that expansion had once been slower, but at some point had begun to accelerate. At first, this was difficult to understand. Matter still has gravity. Galaxies still attract one another. Galaxy clusters can still form, and stars remain bound within their galaxies. But across sufficiently large distances, another influence appears to take control. The name given to that unknown influence is dark energy. The term may sound as though it describes a mysterious object hidden in the darkness, but dark energy is not observed like a star, a planet, or a cloud of gas. No telescope has photographed a distinct region of dark energy. There is no image showing it flowing through the space between galaxies. Dark energy is inferred from the way the universe behaves. If the distances between large structures are increasing more rapidly over time, then something in the model must cause cosmic expansion to accelerate. The name simply stands in for a cause we do not yet fully understand. The simplest description is the cosmological constant. It does not require a type of particle moving between galaxies, nor does it behave like a wind pushing matter apart. It can be imagined as a property of space itself, a background energy that remains even in regions that are almost completely empty. The important point is how this component behaves. As the universe grows, ordinary matter is spread across an ever larger volume. As the distances between galaxies increase, the average density of matter falls. The same amount of matter must be distributed through more space. Radiation also becomes thinner and weaker. Particles of light are not only dispersed across a larger region, but their wavelengths are stretched as well. The energy carried by radiation therefore decreases even more rapidly as the universe expands. In the simplest model, the cosmological constant behaves differently. Its energy density does not decline as space grows. Every newly expanded region of space contains the same amount of background energy as before. This produces a very slow but decisive change. In the young universe, matter and radiation were far denser, so their influence dominated cosmic evolution. As space expanded, both became increasingly diluted. Dark energy did not need to grow stronger in order to become more important. It only needed to remain constant while everything else weakened. Eventually, the influence of dark energy began to overcome the slowing effect of matter. Expansion stopped decelerating as it once had and began to accelerate, with the difference becoming more pronounced over time. If dark energy truly is a positive and unchanging constant, then the future of the universe is almost entirely determined. Space will continue expanding. Structures already held tightly together by gravity will survive within their own boundaries. But systems that are not gravitationally bound will move farther and farther apart. The Milky Way will not be stretched into a thin ribbon simply because the universe is expanding. Its stars remain bound to the galaxy by gravity. The solar system does not grow along with the distances between galaxy clusters. Expansion becomes dominant only across distances large enough for local gravity to lose its hold. Between galaxies that do not belong to the same bound system, however, the emptiness will continue to grow. Light will need more time to cross those increasing distances. Some regions will eventually recede so rapidly that light emitted from them in the future will never be able to reach us. That does not mean they will immediately vanish from the sky. We will continue receiving light that left them long ago. Over time, however, their signals will become weaker, redder, and harder to detect. Distant galaxies will gradually recede beyond the part of the universe that can remain in contact with us. If an observer were to exist in the unimaginably distant future, their sky might appear far emptier than ours. Nearby groups of galaxies would remain, but most of the wider universe would have drifted beyond the observable horizon, not because those galaxies had ceased to exist, but because their newer light could no longer overcome the expansion of space and reach the observer. While the distances between galaxies continue to grow, the story of stars will still unfold within them. Clouds of gas will collapse and form new generations of stars. Massive stars will burn quickly and end their lives violently. Smaller stars will survive much longer, consuming their fuel slowly across immense spans of time. But the gas available for star formation is not unlimited. Some of it becomes locked inside small stars and stellar remnants. Some is driven out of galaxies or becomes too hot and too diffuse to collapse easily. Over time, the rate of star formation will decline. The universe will not go dark all at once. It will slowly fade. The final stars may continue shining long after most galaxies have stopped creating new generations. When those stars exhaust their fuel, the remaining objects will consist mainly of white dwarfs, neutron stars, black holes, and cold planets. Usable sources of energy will become increasingly scarce. Radiation will continue to stretch toward longer wavelengths. The average temperature of the universe will fall. Matter will become more thinly scattered, while structures that once shone brightly will be separated by ever-widening regions of darkness. This ending is commonly called the Big Freeze, a cold, dark, and extremely diffuse state. The name may suggest a single moment when the universe freezes, but there is no one instant when everything stops at once. It is a prolonged fading in which the differences in energy needed to produce motion and structure become increasingly difficult to find. Unlike the Big Crunch, the Big Freeze has no clearly defined endpoint. Space never reverses and contracts. There is no period in which matter is compressed into a smaller volume. The future simply continues expanding, growing colder and emptier across timescales that are almost impossible to imagine. For many years, this appeared to be the path most consistent with observation. The universe was expanding at an accelerating rate. A positive cosmological constant could explain that acceleration relatively simply, and when included in the model, it also agreed well with many different measurements. Maps of large-scale structure, the cosmic microwave background, and observations of supernova explosions could all be placed within the same picture. Matter formed galaxies. Dark matter helped build the cosmic web. The cosmological constant dominated the later universe and drove space to expand more and more rapidly. That picture did not explain what dark energy actually was. It only showed that a constant value could describe its observed effects reasonably well. In science, a simple model that matches the data is usually retained until there is a clear reason to change it. A constant, by definition, should remain unchanged. Whether the universe is young or old, whether space is smaller or larger, the density of that background energy stays the same. If that assumption is correct, there is no mechanism within the model that would cause acceleration to weaken on its own and then reverse. The universe would never turn back. The gravity of matter would become increasingly unimportant on the largest scales as its density continued to decline. Dark energy would remain constant, so its relative influence would grow ever stronger. A future of endless expansion seemed to follow naturally. Yet that certainty always depended on a single assumption: that dark energy truly is constant. The new observations do not show that expansion has stopped accelerating, nor do they say that dark energy has disappeared. What they suggest is far more subtle. When the history of expansion is measured across several different periods, the influence of dark energy in the past may not have been exactly the same as it is today. The difference remains very small. It becomes more visible only when maps containing millions of galaxies are compared with data from supernovae in the cosmic background. Most of the picture still agrees with the familiar model, but a few points seem to lean away from the path predicted by an unchanging value. That deviation may come from the data itself. One method of measuring distance may contain an error that has not yet been recognized. The way different surveys are combined can also make the signal appear stronger or weaker. There is still no reason to declare that the cosmological constant has been replaced. Even so, the mere possibility that dark energy changes over time is enough to make the future less certain than it once seemed. If the component driving expansion does not remain constant, its influence could grow stronger, become weaker, or even change its nature over time. In that case, the Big Freeze would no longer be the only default ending. A universe that is expanding today could still move toward a very different state in the future if the balance among its underlying components shifts far enough. The new map does not say that space has already begun to turn around. It simply reopens a question that once seemed settled. What happens if the thing we call a constant, was never truly constant at all. The answer lies within the smallest differences between measurements. No galaxy suddenly changes direction, and no crack appears across the sky. The history of expansion simply seems to follow a path that does not perfectly match the one drawn by the simplest model. It is a small difference in the data, but one large enough to reopen the question of how the universe may end. No galaxy suddenly turns around, no crack appears in any region of the sky, and no flash of light announces that the future of the universe has changed. Everything continues as before. Stars keep burning, light still crosses immense distances, and the space between distant galaxies continues to grow. The signal that caught scientists' attention is far smaller. It is only a slight difference between the distances measured by telescopes and those predicted by the familiar model. Most of the points still fall close to where they should. Only a few lean slightly away from the expected path, like the hands of an enormous clock that do not all point to exactly the same time. Viewed one measurement at a time, such a difference would be easy to overlook. It could be noise, a calibration error, or the individual motion of the galaxies being observed. But when millions of sources of light leave deviations in nearly the same direction, the question begins to change. Perhaps the issue lies not with any single galaxy, but with the way space has expanded around all of them. During its first 3 years of observations, DESI used more than 14 million galaxies and quasars to measure the lingering traces of waves in matter from the early universe. This is the largest dataset ever used for this kind of measurement. It allows scientists to follow many layers of history, from relatively nearby regions to light emitted when the universe was far younger than it is today. What is important is that DESI data on their own do not say the old model has collapsed. The measured distances can still be described fairly well by a universe containing ordinary matter, dark matter, and an unchanging form of dark energy. The familiar picture remains intact. Only when DESI is placed beside other sources of information do the unusual contours begin to emerge more clearly. One of those pieces comes from the cosmic microwave background, the ancient light released about 380,000 years after the Big Bang. It is like a very early photograph, taken before stars, planets, or galaxies like those we see today had formed. Tiny temperature differences across that image reveal how matter was originally distributed and provide an anchor for the entire history of expansion that followed. At the other end of the timeline are Type Ia supernovae. They do not look back toward the earliest universe, but instead record expansion during later periods, after galaxies had formed and dark energy had begun to play a more prominent role. The light from each explosion provides an estimate of distance, much like observing a lamp of known brightness and using its apparent glow to determine how far away it is. The 5-year DES supernova program selected 1,635 high-quality events for cosmological measurements. That number does more than add entries to a list. Each explosion serves as a marker from a different period, helping to bridge the gap between the universe's earliest image and the galaxy map being assembled by DESI. The 3 sources of data can be imagined as 3 observers standing at different points along a road. The cosmic background sees where the road begins. Supernovae record milestones along its middle and later stretches. DESI measures the spacing between large structures across billions of years. Each observer sees only part of the journey, but the full story appears when their accounts are placed side by side. If dark energy truly remains unchanged, all 3 stories should connect along a fairly clear path. The universe begins with dense matter. Expansion gradually slows under the influence of gravity, and then it begins to accelerate once dark energy becomes dominant. After that accelerated phase begins, its influence should continue with nearly the same character. Most of the data still follow that path, but they do not fit it perfectly. The distances measured by DESI, the brightness of supernovae, and the anchor provided by the cosmic background seem to agree more easily if dark energy is allowed to change slightly over time. This is not a dramatic shift that suddenly causes space to speed up or slow down. It is an extremely gradual change, just enough to bend the expansion curve a little differently after billions of years. Cosmologists often summarize the behavior of dark energy with a number. Without going deeply into the mathematics, the question behind that number is fairly simple. As space grows, does dark energy maintain the same influence? In the familiar model, the answer is yes. The line describing it remains almost perfectly fixed at one value. The new data allow for another kind of line. Dark energy may once have been slightly stronger or weaker, then changed as the universe grew older. The line is no longer completely flat. It tilts and curves ever so slightly, enough to bring measurements from different eras into better agreement. This does not mean dark energy is definitely evolving. When DESI is combined with the cosmic background, a changing dark energy model is favored over the constant model at a level of about 3.1 sigma. When different supernova datasets are added, the strength of the suggestion ranges from roughly 2.8 to 4.2 sigma. That variation is precisely why the result is intriguing, but not yet a final verdict. Sigma is a way scientists describe how difficult it would be to explain a deviation as random chance, assuming all the original assumptions are correct. The higher the number, the harder it is to dismiss the signal as a coincidence. Yet even a relatively high value does not guarantee that the new model is the right explanation. Because errors do not always come from randomness, an instrument may carry a very small bias. One group of supernovae may be calibrated differently from another. Light passing through dust inside a galaxy may be dimmed in ways that are not yet modeled perfectly. The decision about which objects are included in a sample and which are excluded can also shift the final result. That is why the three major supernova datasets do not produce exactly the same level of evidence. Pantheon Plus, Union 3, and the 5-year DES dataset all measure stellar explosions, but they do not use precisely the same objects or process them in exactly the same way. When each is combined with DESI and the cosmic background, the evidence for evolving dark energy becomes slightly stronger or weaker. Those differences do not necessarily mean that one dataset is correct and the others are wrong. They show that the signal lies near the boundary of what current measurements can distinguish. At that boundary, details that seem very small during observation can influence the way the entire history of the universe is reconstructed. Even so, one point is difficult to ignore. DESI's 3-year dataset is more than twice the size of its first-year dataset. Yet the trend has not disappeared. Additional tests have also failed to uncover a single error that could easily remove it. What first appeared as a weak hint has now become clear enough for scientists to seriously reconsider the component that may govern most of the universe's future. One especially distant measurement reaches back to a time when the universe was only about 3 billion years old. DESI used thin absorption features in the light of quasars to trace matter lying between galaxies. From those features, the team obtained the most precise measurement yet of the cosmic standard ruler at that early stage, with a statistical uncertainty of only about 0.65%. That precision sounds remarkable, but the question of dark energy cannot be settled by a single point. A clock may show the correct time in the morning and gradually drift by evening. To know whether it is truly running incorrectly, it must be followed across many moments. The universe is much the same. What matters is not only the distance measured during one era, but the way all those distances connect into a continuous history. When that history is reconstructed, constant dark energy still lies very close to the data. The new model fits better only under certain combinations. The gap between the two explanations is not large enough to eliminate one immediately, but it is wide enough to open possibilities that once did not need to be taken seriously. Dark energy may be a physical field that changes slowly. It may interact with another component of the universe, or the observed signal may reflect something incomplete in the way we describe gravity. Many different paths can produce nearly the same expansion history. For that reason, the word evolving does not automatically lead to a big crunch. Dark energy that weakens may simply cause acceleration to slow. It could approach another stable state, oscillate, or change without ever making space contract. Current data do not point to one specific ending. They only remove the certainty that the future must continue along the old path. To move from a slight deviation on a map to a universe that eventually turns around, another model is needed, one capable of producing a stopping point. That model must explain why space is still expanding today while also containing a mechanism that can change the outward push enough to reverse it in the future. That is where an ultralight physical field enters the picture. It is not included because telescopes have detected a new particle, but because its extremely slow evolution can produce a curve close to what the data seem to suggest. This field changes so gradually that 1 million years is almost insignificant. Even the entire age of Earth is only a short stretch along its journey. In general, the lighter something is, the more easily it can be disturbed. But the particle proposed in this model is so extraordinarily light that its state may take billions of years to change in any noticeable way. For most of cosmic history, it remains almost motionless. Only after space has been expanding for long enough does that quiet evolution begin to leave a trace. The name given to this candidate is the ultralight axion. It remains a hypothetical particle and has not been detected directly. In the model, its importance does not come from producing an immediate and powerful outward force. It comes from changing slowly enough that dark energy in the past, today, and billions of years from now would not be exactly the same. But a slowly evolving field is still not enough to guarantee that the universe will contract. If it simply weakens and approaches zero, expansion may slow without ever reversing. To produce a big crunch, the model requires a second component, one that has always been present underneath, but is currently hidden. That component is a background energy with a negative value. At present, the contribution from the axion field may be greater, so the combined effect still causes space to expand. Over time, the axion gradually changes while the negative background remains. The balance between them could therefore begin to shift in another direction. The galaxy map has not proven that these two components truly exist. It has only revealed an expansion path that this model may be able to explain. The signal could still fade as new data arrive, and many other models are waiting at the same threshold. But if the deviation is real, the force causing space to grow may never have been a single, unchanging entity. It may be the temporary result of two components existing together, a field moving so slowly that only a universe this old could begin to notice it, and a negative energy background lying quietly beneath. As the balance between them changes, the future of space itself may change with it. Some motions happen too quickly for the human eye to perceive. A planet may take months or years to complete an orbit, while a star can change quietly over millions of years. Yet the model now being studied introduces a physical field that moves more slowly than all of these rhythms, so slowly that the proper clock for following it is not a human clock, but the age of the universe itself. The name given to this candidate is the ultralight axion, or more precisely, an axion-like particle. The term may bring to mind a tiny particle flying between galaxies, but in this story, it is better understood as a field extending throughout space. The field does not shine or gather into a cloud that can be photographed. If it truly exists, it would reveal itself only through the way its energy changes and influences the expansion of the universe as a whole. So far, the axion in this model has not been detected directly. It is included because it can produce the kind of evolution the data seem to suggest. Its characteristic mass is about 2 × 10⁻³ electron volts, so small that it is almost meaningless on familiar scales. It is precisely this extraordinary lightness that allows the state of the field to change over billions of years. Lightness here does not mean that the field travels faster than everything else. In a cosmological setting, it can respond so slowly that it remains almost frozen through most of cosmic history. We can imagine it as a ball resting on an extremely gentle slope. The slope is still there, but when the universe is young and expanding rapidly, a kind of cosmic friction keeps the ball from rolling. Over billions of years, the rate of expansion changes, and that friction gradually weakens. The ball begins to move, not in an obvious slide, but so slowly that almost nothing would seem to happen over the course of 1,000,000 years. Only when two moments separated by billions of years are compared does the change become large enough to tilt the expansion history of the universe ever so slightly. The position of the ball represents the state of the axion field, while its height on the slope represents the amount of energy it contributes. When the ball is nearly motionless, that energy also remains almost constant and can behave like dark energy. As the ball begins to roll, the contribution slowly changes. This is why the axion is used as a form of dynamic dark energy. It does not make space suddenly reverse direction. Instead, it allows the influence of dark energy today to differ slightly from its influence in the past. Over a short interval, the difference is nearly invisible. Extended across billions of years, it could send the future down an entirely different path. However, a weakening axion field alone is not enough to make the universe turn around. If the energy-driving expansion simply fades towards zero, space may expand more slowly without ever contracting. To create a maximum size, the model needs a second component, a background value within the equations describing spacetime, and in this case, that value is negative. The cosmological constant is usually described as a positive background energy, strong enough to accelerate expansion. A negative value reverses its long-term role. This does not mean that some invisible substance is pulling galaxies together with strings, nor is there a central point drawing everything back. It simply means that once this component becomes dominant, space can no longer continue growing forever. Dark energy today can be imagined as two layers resting on top of one another. The upper layer comes from the axion field and currently provides a large enough positive contribution. Beneath it lies the negative background of the cosmological constant. When the two are added together at the present time, the result is still positive, so the universe continues to expand at an accelerating rate. What telescopes observe today is therefore not in conflict with the model. The difference is that the upper layer does not remain unchanged forever. As the axion field slowly rolls down its slope, the energy it contributes begins to shift. The negative background does not need to grow or suddenly appear. It has been present in the model from the beginning. The positive layer only needs to weaken enough for the negative contribution beneath it to become increasingly visible in the overall balance. While the field remains almost frozen, the combined effect can closely resemble a familiar positive constant. Once the field begins to move, dark energy leaves that unchanging state and starts evolving slowly over time. This is the stage that DES and DESI measurements may now be beginning to detect. If that interpretation is correct, we are living during a special era, not because any dramatic event has appeared in the sky, but because a field that remained almost motionless for most of cosmic history has only recently begun changing enough for the data to notice. No one sees the ball rolling. What we see instead are distances between galaxies that do not perfectly match the path predicted by unchanging dark energy. Even if the balance has already begun to shift, the universe would not stop immediately. Space has been expanding for 13.8 billion years and still carries that outward momentum. A ball thrown upward continues to rise even after gravity begins slowing it down. A decrease in speed does not mean that its direction changes at once. It only means that the highest point lies somewhere ahead. The universe behaves the same way in this model. The combined influence of the two energy layers changes gradually, but the distances between large structures continue to increase. Acceleration first grows weaker, and then expansion begins to slow more clearly. It takes an immense amount of time for the overall rate to approach zero. Only at that point does space reach its greatest size. The negative sign is the decisive element. If the cosmological constant were zero, the axion field could gradually lose its influence and leave behind a universe that expands more slowly. If the constant were positive, expansion could still continue forever. With a sufficiently small negative value, once the axion contribution declines, the expansion rate reaches zero and then becomes negative, beginning the era of contraction. That negative background cannot be too large. If it were much stronger, the universe could not have survived and expanded for as long as we observe. In the set of parameters being studied, it is small enough to remain hidden today, yet still capable of determining the future once the axion field changes. The researchers test many combinations of axion mass, the field's initial state, the amount of matter, and the cosmological constant. Each combination produces its own expansion history, which is then compared with galaxy distances, supernovae, the cosmic background, and other measurements. The result is not a single answer. Many groups of parameters still describe the data reasonably well, causing the predicted future to vary significantly. A case with no negative background has not been completely ruled out either. For that reason, the model does not prove that the universe must eventually contract. However, when the researchers use the best-fitting set of values as a reference and allow the model to continue into the future, a finite path appears. The axion field keeps moving. Its contribution changes. The negative background gradually takes control, and the expansion rate falls before changing sign. Under that standard calculation, the total lifetime of the universe is about 33.3 billion years, placing the final endpoint roughly 20 billion years from now. That number is not a prophecy, but the result of an experiment performed with a model. A slightly different axion mass would alter the slope of the field, and the ball might roll faster or more slowly. If the negative background were smaller, the turning point could be pushed farther away, and if future data returned to favoring an unchanging positive constant, the entire summit ahead could disappear. Telescopes still do not see the axion, nor do they directly measure the negative energy background. Everything we observe remains part of the universe's expansion history, preserved in the light of galaxies, supernovae, and ancient radiation. The axion and the negative cosmological constant are only one way of connecting those traces into a story that can be tested. The value of the model lies not only in suggesting that dark energy may change, it also predicts the form that change should take and the kinds of deviations it should leave in increasingly precise measurements. If new maps fail to follow that path, the room available for the model will narrow. If the trend continues to grow clearer, the idea of a field awakening after billions of years will become increasingly difficult to ignore. For now, the universe is still growing. Every distant galaxy shows that we are living in an era of expansion, not collapse. But under the best-fitting set of parameters, the axion field's slow evolution means that the highest point no longer lies infinitely far in the future. It may be only about 11 billion years from today. That point would not be the edge of space or a wall for the universe to strike. It would be the moment when the overall rate of expansion falls to zero, when the distances between faraway regions have just reached their greatest extent. To imagine what might still exist at that time, and what a growing universe would look like just before it changes direction, we must follow the timeline another 11 billion years into the future. The space around us is still expanding. Very distant galaxies continue to move farther apart, while their light must cross ever-growing distances before reaching our telescopes. If the model we have been following is correct, this process will continue for another 11 billion years, longer than the entire current age of Earth. But in this version of the future, expansion no longer stretches on forever. Somewhere ahead lies a limit, the greatest size the universe will ever reach. That limit is not located at the edge of an enormous sphere, nor is it a wall that space will eventually strike. The universe does not need an outer boundary in order to grow or contract. What changes is the distance between regions that are not tightly bound by gravity. Galaxies within the same group may continue orbiting one another, while widely separated groups are carried farther apart as the space between them expands. Reaching that maximum does not require imagining a sudden leap 11 billion years into the future. The change unfolds very slowly, across intervals so immense that each billion years is only a small beat in the motion of the universe as a whole. From the present onward, space continues to grow. If galaxy maps could be redrawn after extremely long spans of time, they would reveal the same broad structure, but with the largest voids stretched wider than before. Under the model's best-fitting set of parameters, the scale factor of the universe, at its maximum, may reach about 1.69 times its present value. This does not mean that every object will be stretched by the same proportion. A planet will not swell into a larger world. Living bodies will not be pulled apart, and atoms will not become wider simply because space is changing on cosmic scales. Local forces will continue to preserve the sizes of ordinary structures. Electromagnetism keeps atoms and molecules stable. Gravity holds planets around stars, stars within galaxies, and many galaxies within the same group. Expansion becomes clearly visible only across distances so vast that these local bonds are no longer strong enough to overcome the changing scale of space. The figure of 1.69 therefore describes the distance between extremely remote structures, not the size of individual objects. It is the model's way of expressing how cosmic distances change together over time. During the first few billion years of that journey, the slowing may not be easy to recognize. A civilization observing for a few thousand or even a few million years would see almost the same trend. Only by comparing moments separated by billions of years would the expansion curve reveal that it was gradually losing the speed it once had. The reason lies in the balance built into the model. The ultralight axion field continues moving along its extremely gentle slope, slowly changing the positive energy contribution. The negative energy background does not need to appear later, because it has been present in the equations from the beginning. As the positive contribution declines, the negative part becomes increasingly difficult to conceal, and the expansion of space begins to slow. There is no clear moment when the entire universe somehow realizes that it is losing momentum. The transition is much gentler than that. First, the acceleration weakens. Expansion then continues, but at a gradually decreasing rate. The distances between remote galaxies still grow, yet each new interval of time adds less separation than the one before. Perhaps the closest image is an object thrown upward. Gravity pulls downward from the moment it leaves the hand, yet the object continues rising because its initial motion has not disappeared. The universe in this model also carries the momentum of an expansion built up across an immense history. The negative energy background may already be weakening that motion, but billions of years are required for the overall expansion rate to fall to zero. Throughout that time, everything inside galaxies continues along its own path. Stars with fuel still shine. Planetary systems continue orbiting their stars. Galaxies may merge, change shape, or create new generations of stars if enough gas remains. The universe does not wait for its maximum size in a motionless state. It remains filled with local activity even as its overall scale approaches a moment of stillness. That is what makes the maximum so difficult to imagine. We often associate a turning point with a violent event, but here there is no explosion, no unusual flash, and no signal appearing across every sky at once. A distant planet still completes its orbit. A photon continues traveling through space. Only the expansion rate of the universe as a whole has reached zero. At that moment, the universe is neither empty nor motionless in the ordinary sense. Gravitationally bound structures continue to move. Light still travels. Physical processes continue inside every galaxy. The only thing that has stopped is the growth of distances on the largest scales. After tens of billions of years of expansion since the beginning, the scale of space has reached its greatest value. The maximum does not last as a stable era. In the language of the model, it is only the point where the sign of change passes from positive to negative. Before it, distances are still increasing. After it, they begin to decrease. Between those two directions lies an exceedingly thin slice of cosmic history. At first, the contraction would be so slight that it would be almost indistinguishable from complete stillness. An observer inside the universe would not see galaxies suddenly rushing back. A distance that had once been increasing very slowly would only just begin to shrink at an even slower rate. On the scale of a single galaxy, ordinary motions would still overwhelm any sign of the larger change, but the direction would already have reversed. Once the scale factor begins moving downward instead of upward, the entire future enters a different path. Distances between remote regions gradually shrink. The density of matter no longer declines forever. Radiation that was stretched during expansion will eventually experience the opposite effect as space contracts. None of this can be observed directly today. Telescopes see only an expanding universe and collect light from eras that have already passed. The maximum point, roughly 11 billion years from now, appears only after the data are placed into a model, its parameters are selected, and its evolution is extended forward in time. That date is therefore not fixed. If the mass of the axion field were different, its motion along the slope would also change. If the negative energy background were smaller, the stopping point might be pushed farther away. If dark energy is truly constant, the entire moment of maximum expansion would disappear, and space could continue growing forever. Even the figure of 1.69 belongs only to the best-fitting parameter set. Other values could move the turning point farther into the future or prevent it from appearing on a similar timescale. The model shows only that a finite path may still be compatible with some of the data available today. What makes that path remarkable is the way it connects two states that appear to be opposites. Today, the universe is still expanding at an accelerating rate. In the distant future, that same universe could slow down and begin to contract. No collision from outside is required, and no new force needs to appear suddenly. The balance among components already present only needs to change slowly enough across billions of years. From our present position, 11 billion years seems impossibly distant. But for the ultralight axion field in the model, it is simply the time required for its state to change by the necessary amount. Something that appears almost motionless on every familiar timescale may still become decisive when the clock is measured by the age of the universe. A future in which all of space reverses direction does not begin with a great event, but with the smallest motion of a field that has never been seen. That motion accumulates quietly, weakening the outward push until the expansion carried forward from the early universe finally runs out of momentum. At that summit, everything continues moving in its own way. There is no center for galaxies to fall toward and no outer edge for space to close around. There is only the greatest distance ever reached, and a negative sign appearing in the rate of change of the universe as a whole. Afterward, that negative sign grows more pronounced. Distances that once expanded begin to shrink, almost imperceptibly at first, then more rapidly through the eras that follow. The universe is no longer moving toward an infinitely cold and diffuse future. It has passed its highest point and begun its journey inward. From that moment on, the question is no longer whether expansion will stop. The new question is what happens when space itself begins to contract, and how that first nearly silent change could eventually carry matter, light, and every surviving structure toward an entirely different ending. Imagine the entire history of the universe as one immensely long breath. From its initial hot and dense state, space has been opening for about 13.8 billion years, carrying galaxies farther apart and allowing light to spread across ever greater distances. If this model is correct, that breath will continue for billions of years more, slowing until it reaches an almost perfect pause. After that silence, the direction of motion reverses. Space begins to turn inward. The first moment of contraction would not resemble an event that any observer could easily recognize. Galaxies would not all stop at once and then rush back toward us. No signal would travel across the universe announcing that the era of expansion had ended. A distance that had been increasing very slowly would only just begin to decrease, at a rate initially so slight that it would be almost indistinguishable from stillness. Contraction also would not mean that every galaxy was moving toward some central point located in the middle of the universe. If an observer existed in a distant galaxy, they would not see themselves approaching any special center either. From any location, sufficiently large distances could gradually begin to shrink. Matter would not be moving through a fixed room. The scale of the room itself would be changing. We can imagine galaxies as points marked on an elastic surface. As the surface stretches, the points move farther apart, even though they do not travel across it on their own. As the surface contracts, the distances between them decrease. This comparison only helps us sense the motion, because the universe does not truly rest on a sheet of rubber, nor does it require an external space into which it can contract. What matters is distance itself. Before the maximum point, two regions not bound together by gravity tend to move farther apart over time. After the maximum, that overall tendency reverses. They begin to draw closer, not because each galaxy receives some command to turn around, but because the scale of the space between them is decreasing. During the earliest stages, the individual motions of galaxies would still be far greater than the signal of contraction. Some galaxies would already be approaching one another because of gravity. Others would continue moving in different directions within their clusters. Planetary systems would keep orbiting, stars would still travel around the centers of their galaxies, and light would continue crossing space. On smaller scales, the universe would seem almost unchanged. Only across the greatest distances would the new direction become visible. Regions once carried apart by expansion would no longer continue separating. The emptiness between them would shrink little by little. If the cosmic map could be redrawn after hundreds of millions or billions of years, large structures would appear closer together than they had before. This transition begins almost silently, but it does not remain slow forever. As space becomes smaller, the same amount of matter is contained within a reduced volume. The average density, therefore, rises. Regions that were once extremely sparse no longer continue thinning out, while gravity between large structures gradually becomes more significant as their separation decreases. The negative energy background in the model continues to influence the evolution of the universe as a whole. It does not pull individual galaxies with a force pointing in one particular direction. Its influence lies in the way space-time behaves collectively. Once the positive energy from the axion field is no longer dominant, the tendency toward contraction may not only continue, but gradually accelerate. At the maximum point, the rate at which space changes has just reached zero. Immediately afterward, it takes on a very small negative value. Over time, that value becomes more pronounced. Distances shrink more rapidly, density rises more quickly, and the collapse begins to reinforce itself through the very conditions it creates. During expansion, matter moves increasingly far apart and the universe grows colder. Light traveling through expanding space is stretched toward longer wavelengths and carries less energy. When the direction reverses, these trends also begin to change. Distances become smaller. Light is no longer stretched in the same way. The background temperature of the universe may begin to rise. A photon traveling through contracting space tends to be compressed toward a shorter wavelength. It can be imagined as a set of ripples being pressed closer together as the space containing them shrinks. The light therefore carries more energy than before. Radiation that cooled through billions of years of expansion begins to warm again, very slowly at first, then more noticeably as contraction accelerates. This change would not immediately create a hot, glowing sky. During the early phase of contraction, the universe would still be unimaginably vast. Galaxies would remain separated by immense distances, and many stars would already have passed through most of their lifetimes. Only the long-term direction would have reversed. The process that once made everything colder and more diffuse would now gradually lead toward a denser and hotter state. This would not be the Big Bang played backward, like a film running from end to beginning. Stars that had burned through their fuel would not somehow recover it. Galaxies that had merged would not separate and return to their original forms. Objects that had collapsed would not unfold into their former states simply because cosmic distances were decreasing. History leaves behind changes that cannot be erased by reversing expansion. Energy has dispersed, matter has undergone countless reactions, and stars have transformed lighter elements into heavier ones. The universe may become hot and dense again, but it would not return to the exact version that existed during its earliest moments. A room that has grown cold does not restore every former motion when it is heated again. Shattered pieces of glass do not reassemble into a cup simply because time is imagined in reverse. The same is true of the universe. Entropy does not disappear when space begins to contract. Contraction creates a new future, not a perfect repetition of the past. This makes the collapsing phase profoundly different from a reversed Big Bang. By then, the universe would be older. Many stars would have gone dark. Many galaxies might have passed through collisions and mergers. Matter would carry the full record of its history as it entered an increasingly smaller space. As distances between large structures continued to decrease, regions that had once been isolated might begin approaching one another again. Yet this would not mean that everything immediately collided. Space would still be vast, and these motions would unfold over enormous spans of time. The focus of the model is not each individual encounter between galaxies, but the overall trend carrying all matter and radiation into a smaller volume. Long enough after the turning point, contraction would no longer be a subtle detail on a curve. Rising density would make the gravity of matter increasingly important. Large distances would shrink more rapidly, while radiation continued to be compressed. Conditions once associated with a cold and diffuse universe would gradually be replaced by an environment that was becoming hotter and denser. Even so, no one today can observe this phase directly. Telescopes record only a universe that is still expanding. Contraction belongs to a future inferred by the model, based on the assumptions that dark energy truly changes and that a negative energy background will eventually become dominant. If either assumption is wrong, the turning point may never arrive. Even if contraction does occur, the details farther ahead would remain beyond our ability to test. Present equations can follow the process while density and temperature remain below the most extreme conditions. Closer to the end, the universe would enter states increasingly unlike anything we have ever measured. Quantum effects of gravity, for which no complete theory yet exists, could alter the outcome. The process may continue toward the kind of collapse predicted by the classical model. Or undiscovered physics may produce a different transition before the universe reaches its final limit. Present calculations reveal a possible direction, but they do not necessarily disclose everything that would happen in the final moment. What can be said within the limits of the model is that contraction would not begin in chaos. It would begin with a tiny change in the motion of space as a whole, so slight that it would be almost hidden beneath every local movement. A distance would stop increasing. Then, it would begin to shrink, just a little. Over billions of years, that faint signal would gradually become the dominant trend across the entire universe. There would be no clear boundary between the final day of expansion and the first day of collapse. There would only be an exceedingly thin point on the timeline, where the overall rate passes through zero. Before that point, the cosmic breath would still be opening outward. After it, the breath would begin turning inward, carrying with it every structure formed throughout the long history that came before. As time continued, light, matter, and the empty spaces between them would be drawn into an ever smaller volume. Temperature would rise, density would increase, and the collapse would gradually accelerate. The Big Crunch, then, would not suddenly appear in the final second. It would be the ending of a process lasting billions of years, beginning with the almost silent moment when space first changed direction. The Big Crunch is often imagined as an explosion in reverse, with galaxies all turning around at once and rushing toward a point at the center of the universe. It is an easy image to remember, but it is not entirely accurate. In this scenario, there is no single center waiting for everything to fall into. Every place becomes closer to every other place because the distances within space itself are shrinking. If an observer could stand in a very distant galaxy and look around, they would not see themselves moving toward any special location. They would simply notice that the largest distances were decreasing. The same would be true from our own galaxy. No place would be the center of the collapse, and there would be no region outside the universe from which to watch it close in like an object viewed from afar. The Big Crunch, then, is not the collapse of something contained within space. It is the contraction of space-time itself on a cosmic scale. Galaxies, galaxy clusters, light, and matter are not being forced toward a pre-existing point. They are all taking part in a process in which the scale separating distant regions becomes progressively smaller. The model's timeline can be summarized fairly simply. The universe is now about 13.8 billion years old. It may continue expanding for nearly another 11 billion years, reach its maximum size, and then contract for close to 9 billion years. Its total lifespan would be about 33 billion years, meaning that under the best-fitting set of parameters, the endpoint would lie roughly 19 to 20 billion years from today. During expansion, matter is spread across an ever larger volume. Light is stretched toward longer wavelengths, the background radiation cools, and regions that are not gravitationally bound move farther apart. As space contracts, those trends gradually reverse. The same amount of matter is contained within a smaller volume. Large distances decrease, and light begins to be compressed. At first, the change would be extremely slow. Just after the point of maximum expansion, the universe would still be so vast that galaxies could continue along their own histories for a very long time. The remaining stars would still shine. Systems held together by gravity would continue moving much as before. Only on the largest scales would contraction appear as a broader trend. Over time, that trend would become clearer. The density of matter would rise as the volume decreased. Gravity between large structures would gradually gain influence, while the negative energy background in the model continued driving the scale factor downward. Contraction would not remain at its initial pace forever. It would accelerate as the universe moved deeper into its shrinking phase. Radiation would respond even more strongly than matter. As space contracted, wavelengths would be pressed shorter, increasing the energy carried by light. The background radiation, which had cooled through billions of years of expansion, would begin to warm again. At first, the increase would be almost impossible to detect, but as the scale of the universe decreased more rapidly, the overall temperature would rise more clearly. As contraction continued, the curvature of space-time would increase. In general relativity, Matter and energy determine how space-time bends, while that geometry guides the motion of matter. As density grew, the geometry of the universe would become increasingly extreme. The equations could still trace the overall trend, but they would be pushed into a regime that has never been tested directly. In the classical model, the Big Crunch leads toward a state in which the scale factor approaches zero. Temperature, density, and curvature rise to extraordinarily large values. If the same equations are extended without modification, they eventually lead to a singularity, a point at which the familiar description stops working. The word singularity can create the impression that science has discovered a specific object waiting at the end of time. In reality, it often signals that the theory being used has reached its limit. When an equation produces infinite values, that does not necessarily mean nature truly contains an infinite point. It may simply mean that the current model is no longer sufficient to describe such extreme conditions. The closer the model moves toward the end, the more extreme its numbers become. Yet, at the very place where we might expect the most certain answer, science must acknowledge its greatest limitation. The equations may follow the universe as it contracts toward ever smaller scales, but they cannot guarantee that the final picture remains accurate once every familiar scale has been exceeded. General relativity describes gravity extremely well across the scales of planets, stars, galaxies, and even cosmic evolution. Quantum mechanics describes the smallest world with extraordinary precision. In the final stage of a Big Crunch, however, enormous density would force both realms to appear at once. A complete theory of quantum gravity would then be required, and no such theory has yet been fully verified. For that reason, the endpoint of the classical model may not be the true endpoint of nature. A quantum effect may prevent space-time from being compressed without limit. The collapse may pass into another state, or lead to a bounce rather than an absolute ending. Such possibilities appear in many models, but they remain far beyond observational evidence and cannot yet be treated as conclusions. The research being followed here does not attempt to solve the entire mystery of the final instant. Its goal is more modest, though still bold, to use current expansion data to determine whether a model can carry the universe to a maximum size and then into contraction, and how long that process might take. The figure of roughly 33 billion years refers to the path toward collapse, not to a complete explanation of what happens when the classical equations cease to apply. Today's telescopes do not see the Big Crunch. They see only a universe that is still expanding, distant galaxies, supernova explosions, and ancient radiation. There is no direct observation of a contracting phase. The entire future is inferred by choosing a model, placing the data within it, and allowing the equations to evolve forward in time. If the negative energy background truly exists and eventually becomes dominant, the general path may be correct. The universe would reach its maximum size. Expansion would stop, and the scale factor would begin to decrease. Matter would become denser, radiation would grow hotter, and large distances would shrink until the model approached an extreme state. If dark energy does not change, this story will never unfold. If the signal in the DESI and supernova data is only a statistical fluctuation or a systematic error, the turning point may disappear. If the ultralight axion does not exist, or if the cosmological constant is not negative, the Big Crunch would no longer be the ending favored by this model. Even if the early part of the model is correct, the precise timing could shift enormously. A small change in the parameters of the axion field could make it evolve faster or more slowly. A different negative background value would alter the time required for expansion to stop. The total lifespan is therefore not a number carved into the structure of the universe. What makes the Big Crunch worth contemplating is not the image of everything being crushed in a single instant. It is the slow transformation of the entire background of space-time. The process begins with a small deviation in the history of expansion, passes through an almost silent maximum point, and continues for billions of years before conditions become extreme. There is no clear boundary where the ordinary universe ends and the Big Crunch begins. The collapse has already started the moment the scale factor passes its peak and begins to decline. Later stages only strengthen that tendency, until light, matter, and the full geometry of space-time are drawn into the same contracting motion. For most of the journey, the Big Crunch would not yet resemble an apocalypse. It would look more like a cosmic future, gradually changing state. Only much later would density and temperature rise high enough for familiar descriptions to fail. The drama would not lie in one final explosion, but in the fact that all of space had changed direction and continued moving ever deeper along that path. Yet, this distant prediction begins with very specific measurements: the positions of galaxies, the brightness of supernovae, the cosmic background, and ancient ripples in matter all contribute to the expansion history that the model is trying to reproduce. From that history, researchers choose values for the axion field and the negative cosmological constant. They test many possibilities, retain those that agree more closely with the data, and then examine where each set of values leads the universe. One parameter set produces a total lifespan close to 33 billion years. Another may give a longer or shorter result, or may not produce a big crunch in the same sense at all. 33 billion years therefore sounds more precise than the certainty it truly carries. It is not a date read directly from the sky. It is the outcome of a chain of choices: which data are used, which model is tested, which parameters provide the best fit, and how far the equations are extended into the future. To understand the real meaning of this prediction, we cannot look only at the endpoint. We must return to the entire process that produced the number, from the light of distant galaxies to the way an expansion curve is fitted to the data. Before asking whether the universe will truly end after about 33 billion years, we first need to understand how that number was calculated. The more specific a number sounds, the more certain it can feel. 33 billion years seems like a result read from a cosmic clock with perfect precision. In reality, it is the endpoint of a path built from data, models, and many assumptions. If even one part of that path changes, the ending could shift far into the future or disappear entirely. Researchers do not observe the lifespan of the universe directly. Telescopes collect only light from galaxies, quasars, and supernova explosions, along with the background radiation left over from the early universe. Each source reveals one part of cosmic history, from the time when space was still very young to the era of accelerated expansion we see today. Redshift shows how much light has been stretched during its journey to Earth. The brightness of supernovae helps estimate distance. The positions of millions of galaxies reveal how matter has been distributed and how far structures have moved apart. When these measurements are combined, a history of cosmic expansion gradually emerges. Most of that history still lies close to the familiar model, in which dark energy does not change over time. Some points, however, do not fit perfectly, especially when DESI data are compared with supernova observations and the cosmic background. The deviations remain small, but they are large enough for scientists to explore another explanation. In the model that leads to the figure of 33 billion years, dark energy is no longer an unchanging value. It is described by an ultralight axion field evolving extremely slowly, combined with a negative cosmological constant. The axion field allows the model to reproduce a slight change in the expansion history, while the negative energy component opens the possibility that space may eventually reverse direction. Neither component has been observed directly. Telescopes do not see the axion, nor do they measure a negative cosmological constant. These elements are introduced into the model only to test whether they can explain the data more successfully. After choosing the model, researchers vary the values within it. The axion mass can be larger or smaller. The field may begin in a different initial state. The negative energy background can also take on different strengths. Each combination produces its own history of the universe. Some combinations allow space to continue expanding for a very long time. Others cause expansion to slow earlier. Some lead to a big crunch, while others do not produce a turning point on a similar timescale. These possible histories are then compared with observational data. The set of values that produces an expansion curve closest to the measurements is called the best-fitting parameter set. That name does not mean scientists have found the one true set of values belonging to the universe. It means only that, among the possibilities tested, this set currently agrees with the data slightly better than the others. Many other parameter sets may still lie very close to the observations. They have not been completely ruled out, and they can lead to different futures. For that reason, best fitting does not mean certainly correct. Once a reference set of parameters has been selected, researchers allow the model to continue beyond the present. At first, the universe keeps expanding. The axion field changes slowly, the positive energy contribution gradually declines, and the negative background becomes increasingly important. About 11 billion years from now, the expansion rate in the model falls to 0. This is when the scale factor reaches its maximum value. Afterward, the rate changes sign, space begins to contract, and the universe continues shrinking for nearly 9 billion years. When the scale factor approaches 0 in the classical description, the total time since the universe began expanding reaches about 33 billion years. Because the universe is already around 13.8 billion years old, that endpoint would lie roughly 19 to 20 billion years from today. The figure of 33 billion years was therefore not placed into the model at the beginning. It emerged only after a sequence of steps: gathering data, choosing a model, adjusting its parameters, finding the best fitting path, and then extending that path into the future. If even one link in that chain changes, the result changes as well. A different axion mass could make the field evolve faster or more slowly. A weaker negative background could push the turning point farther away. If dark energy is truly constant, the big crunch would not occur in this way. The result also depends on how different data sets are combined. When DESI is paired with different supernova samples, the evidence for evolving dark energy is not exactly the same. Some combinations strengthen the signal, while others make it weaker. Those differences may come from the way supernovae are selected and calibrated, from the effects of dust within galaxies, or from small errors that have not yet been recognized. A very slight deviation today, when extended across tens of billions of years, can significantly change the predicted time of the ending. It is therefore important to separate 3 layers of the story. What has been observed is the expansion history of the universe, along with several small deviations from the simplest model. The ultralight axion and the negative cosmological constant are one model's explanation for those deviations. A big crunch, after a total lifespan of about 33 billion years, is an extrapolated result, not something that has been proven. Scientists have not discovered the date on which the universe will die. More precisely, a model that agrees with some of the new data allows for a reference estimate of roughly 33 billion years for the universe's total lifespan. This uncertainty does not make the research less valuable. A good model does more than explain what has already been observed. It also tells scientists what they should look for next. If dark energy truly evolves in the predicted way, future galaxy maps should continue to reveal the same trend. If the signal becomes clearer, the allowed range of parameters will narrow, and the time of maximum expansion may be estimated more consistently. If the deviation fades, the axion model with a negative energy background will lose support, and the figure of 33 billion years may no longer hold. What is remarkable is that we do not need to wait 20 billion years to test the prediction. If that future is real, its traces are already present in the light reaching our telescopes today. The extremely slow evolution of dark energy must leave a particular pattern in the distances between galaxies across different periods of cosmic history. New observatories will not see the big crunch. They only need to measure the universe precisely enough to distinguish unchanging dark energy from a component that is evolving very slowly. The most distant future of the universe may therefore be decided by measurements made within our own generation. No telescope can see the big crunch. If that moment truly exists, it still lies nearly 20 billion years in the future. Yet we do not need to observe the endpoint to test the path that might lead there. If dark energy is changing, traces of that evolution are already present in the distances, light, and distribution of the galaxies we observe today. That is why the story returns to DESI. Its current map is still incomplete, and every new layer of data may bring the expansion history into sharper focus. If the deviations continue to appear as the number of measured galaxies increases and the uncertainties grow smaller, the idea of unchanging dark energy will face an increasingly serious challenge. The signal could also fade. Some of the points that now lean away from the familiar model may return to their expected positions once the data are calibrated more precisely. In that case, a positive and constant cosmological constant may remain the simplest explanation. while the possibility of a universe that eventually turns around would lose much of its observational support. What matters is not any single measurement. DESI's data come from millions of galaxies, but even an enormous map can still carry small biases. To determine whether the signs of evolving dark energy are real, scientists need several independent methods examining the same question. One telescope may measure distances. Another may track the shapes of galaxies. One survey may record stellar explosions, while another searches for the extremely slight bending of light as it passes through regions containing large amounts of matter. When different methods all point in the same direction, the likelihood that the result is merely an error becomes smaller. Euclid is part of that test. Rather than searching for dark energy as an object, it observes how billions of galaxies are distributed across the sky, and how their shapes are subtly distorted by matter lying between us and those sources of light. These tiny distortions create another layer of the map, revealing not only where galaxies are located, but also how matter has gathered over time. If dark energy changes, it affects more than distance. It also alters the rate at which large structures form. Regions of matter may grow slightly faster or more slowly than the constant dark energy model predicts. Euclid therefore does not need to see dark energy itself. It only needs to follow the traces dark energy leaves on the shape of the cosmic web. On the ground, the Vera C. Rubin Observatory will watch the sky with a different rhythm. Rather than photographing a region once and moving on, Rubin will repeat its observations night after night and year after year. The sky will no longer appear as a still image, but as a very long film of objects brightening, fading, or changing position. The supernova explosions appearing in that film will be especially important. They are like lamps being switched on at immense distances, allowing scientists to measure the later history of cosmic expansion again. Some explosions are seen as they occurred when the universe was younger, while others belong to periods closer to the present. When enough events are placed side by side, the expansion curve can be traced in finer detail. Rubin will also help map matter through weak gravitational lensing. Light from distant galaxies is bent slightly before reaching us. The effect is too small to detect reliably in any single galaxy. But when millions of images are analyzed together, a broader pattern can emerge. The Nancy Grace Roman Space Telescope will add another perspective. From beyond Earth's atmosphere, it will be able to track faint sources with greater stability while observing many galaxies and supernovae across wide areas of the sky. Roman will not replace DESI, Euclid, or Rubin. It will provide another independent dataset for testing whether the same expansion history appears. A result becomes truly convincing only when it does not depend entirely on one instrument or one method. If DESI measures distance in one way, Rubin and Roman use supernovae in another, and Euclid follows the growth of structure. All of them must tell stories that can be connected. SphereX will observe the sky in infrared light, where many features that are difficult to see at ordinary wavelengths become clearer. By mapping light across nearly the entire sky, it can add information about distance, the distribution of galaxies, and the history of structure formation. Each instrument holds only one part of the story. DESI reads redshifts from millions of sources. Euclid follows galaxy shapes and the bending of light. Rubin records how the sky changes over time. Roman observes supernovae and large-scale structure from space. SphereX adds a vast infrared map. What scientists need to find is not one isolated anomaly, but a consistent pattern. If dark energy truly evolves, its influence must appear across several layers of observation. Galaxy distances should change in a particular way. The rate of structure formation must respond as well. Supernovae, gravitational lensing, and infrared maps cannot tell completely contradictory stories. If several methods all begin to lean away from the constant dark energy model, the current signal will no longer be only a small deviation in DESI data. It will become a problem that the standard model must address. Dark energy may then no longer be describable by one simple, fixed value. This would not automatically prove that an ultralight axion exists. Another physical field might produce a similar expansion history. Our description of gravity on cosmic scales may need adjustment. It is also possible that several unknown components combine to create an effect resembling evolving dark energy. Even so, If the evolution curve truly emerges, endless expansion will no longer be the only default future. The big freeze may still occur, but it will have to compete with other possibilities. Among them, the big crunch would return as a serious physical scenario, not because contraction had been observed, but because a model could connect present-day data to a future turning point. If the signal disappears, the figure of 33 billion years will not become entirely meaningless. It will still record a period when the data opened a new path and forced science to test assumptions that had once seemed secure. A model may fail to become the correct description of nature and still remain valuable if it reveals what needs to be measured and helps observations become more precise. That is how science moves forward. A small deviation appears. A model is built to explain it. The model produces specific predictions. New telescopes test those predictions. In the end, the path may either widen or close. Under the current best-fitting set of parameters, the story contains 3 main milestones. The universe has already passed through about 13.8 billion years. It may continue expanding for nearly another 11 billion years before reaching its maximum size. After a period of contraction, its total lifespan may end near the 3 billion year mark. These numbers are not confirmed milestones. They belong only to a model that is still being tested. If dark energy is constant, the maximum point will never appear. If the axion does not exist, or the background energy is not negative, the future will follow another path. What is remarkable is that the difference between these futures may be hidden within the smallest uncertainties in present-day data. A few parts in 1,000 in distance, an extremely slight distortion in a galaxy's image, or a subtle change in the brightness of a supernova may determine whether the expansion curve continues upward or eventually turns downward. We live within only a tiny slice of that history. A human lifetime is an almost invisible moment on the cosmic scale. Even the entire history of civilization occupies only a minute fraction of the billions of years that have already passed. Yet from this brief position, human beings can collect light that began traveling through space before Earth had formed. We measure its wavelengths, compare its brightness, reconstruct distances, and trace how matter gathered across many different eras. None of us can wait until the universe reaches its maximum size. No civilization could observe the entire expansion process across tens of billions of years. But equations in ancient light allow us to assemble separate moments into a history and then attempt to extend that history into the future. The universe may expand forever. Galaxies may continue moving apart, the final sources of light may slowly fade, and space may enter an ever colder, darker, and more diffuse future. Or the universe may be approaching an invisible summit, where expansion slows, comes to a stop, and then begins to reverse. For now, both futures remain hidden within the very small uncertainties of our measurements. No one knows whether the cosmological constant is truly positive, 0, or negative. No one knows whether the ultralight axion exists, and no one knows whether the figure of 33 billion years will survive once the new maps are complete. That number may become increasingly clear, or it may disappear, giving way to a future with no turning point. Whatever the final result may be, what matters is not only a prediction about the universe's end, it is the fact that living beings on a small planet, occupying one brief moment in history, have learned how to read the motion of millions of galaxies. From light that has traveled through space for billions of years, we do more than retrace the past. We also attempt to look into the second half of the universe's entire life.